Hey everyone, welcome back. Today we're going to start a new project. This one's going to be shorter and sweeter, but it's still going to take a couple parts. It is going to be creating generative maps in TouchDesigner. So let's take a look at where we may end up. This is one possible edition, or a rendition rather, of where we might end up here. A couple of different features that we will build an ability to play with. That'll be something like this, which kind of looks like a time lapse or countries changing over time. Um, Also results in more or less detailed subdivisions. This one is an unexpected effect that I actually really like, and that is this position quantization, which we'll get into, that results in a pretty cool geometric look where these paths kind of appear and create themselves in real time. And we will, of course, discuss exactly how all of that is done in depth. We'll be able to add a little bit of interesting post. And then one thing that we will develop even further than I have right now is a way to change some of these colors independently of the others. And that'll be using different layers to extract and interact with those bits of information. So that is an example and short overview of where we're going. Here is a quick look at the network. We'll use a procedural terrain input. That's going to form the basis of our generative map. Then we're going to, in part 2, create this replicator network to extract our different map layers. This is where I mentioned we would be able to actually have some of these map layers behave differently from others. So for example, we can shade or not shade some of the edges from different layers. This will allow us to have some pretty cool effects and potentially incorporate things like audio reactivity pretty well. So, something to keep in mind. Then we're going to do just a little bit of comping here to build up to our final output. And we'll do a little bit of post to get things looking real nice. So that's it. Like I said, this project is going to overall be pretty short compared to some of the other series. I'm just going to break it into a couple smaller videos to make things digestible. So today we're going to look at one component, really like the new component for this entire network, and that's the jump flood algorithm. I'm actually going to start by creating a separate effect that we actually aren't looking at here that's going to help us understand what the jump flood algorithm does. And then we will use that in part 2 in depth because each of these layers has a jump flood algorithm component. So yeah, it'll help to have some good basic understanding of what that does, which we'll develop in this video, and then go on in the next video to put everything together and get to this cool end result. I really like this one. It's pretty unique, I think. So, anyway, let's get started. All right, so I will get rid of this, move it over here, get a empty container, call this GenMaps Live, and then I will just go inside, give myself an out, fire that in, and now I have a container that I can start building with. Now, first things first, you are going to need, if you want to follow along exactly, the procedural terrain that is not here. It should be. Uh, nope. Here we go. This one. So, if you haven't gone through this tutorial yet, I recommend you do so and build this procedural terrain component. It's really just a noise algorithm, but it is using a special noise generation technique that is specifically intended to develop terrain-like features. So I'm going to use that. That's what gives us our great realistic map looking quality. So follow along and create this if you haven't yet, or just go grab it on Patreon if you prefer. We will come back to the rest of this. I will just drop down my noise procedural terrain and simply grab this terrain. So I guess now is as good a time as any to parameterize our output resolution. That's all we'll need for now. So first things first, I want to create a short little feedback loop. And this short little feedback loop is going to basically just displace our terrain by its slope, just like that. And boom. So one thing that I do want to do is parameterize this feedback pulse. A technique or a trick that I recently learned is using the parent shortcut here. So I'm just going to name the parent shortcut P. Then my feedback pulse, I will drag and drop onto my customized component editor. And now you'll see that because I have a parent shortcut set, instead of having this reference be parent like this, it is referencing the component with the parent shortcut name of P and grabbing the reset pulse parameter from there. That is helpful because if I then collapse these components into a base, my feedback pulse is still pointing at the top level parent reset pulse parameter, and you don't have the super annoying thing where when you drop down some components into a base, you lose all of your parameter references that were originally pointed at the top level parent. So, quick tip, something that again I just learned, I wish I knew it longer, super helpful. Anyway, now I will just open up my parent parameters. I'm going to point this pulse at my local parameter, my local component. And the pulse parameter, I have a video that's free for everyone on YouTube about my local component and how I have some global shortcuts set. So you can go check that out if you're interested in learning more or are confused by what just happened. But now I can just press 1 on my keyboard and reset our feedback. I don't have to do much to this displace. I'm just going to drop the weight down to something like 0.1. And now, yeah, we can see that our terrain is being displaced over time by its slope. Why do I like this? It becomes a little bit more apparent if I throw an edge down, and maybe we'll just display this here. So we can see that as our displace is happening and working iteratively in the feedback loop, our terrain is naturally being pushed towards these edges, which are really, you can think about them kind of like valleys that are filling with a sediment. Now, this isn't a perfect erosion. There's a lot of things that are not physically correct about it, but the idea is there. So we can think about it as kind of approximation of erosion, or maybe you want to think about it as like erosion in pixel space. I don't really know. Not precise, but kind of makes sense. Anyway, I like that it pushes the terrain to form these long seams, which I think look a lot like rivers or valleys or maybe ridges, depending on which way they point, which are common features in maps and obviously very common as border features, right? Tons of countries have rivers that form their borders. Mountain ranges are also very common as far as border formation, as are deep ravines. So I like this because it emphasizes some of those characteristics and I think leads to an organic, kind of naturally occurring feel. Now, I don't need this edge. Actually, that's not true. I do need this edge. I'm going to keep that edge. And I'm going to also insert a limit. This limit we will quantize by rounding. And what that does is simply, if I just add a noise, it might be a bit easier to see. What the quantize does is round the values to the nearest step size. So we're getting this banding with regular noise because every value is being rounded to the nearest, in this case, 0.3. And that is what is leading to these kind of isoline effects that we're seeing. So if we apply the same thing to our terrain, we're essentially rounding or thresholding or terracing our terrain with this step size. And then we can see with the edge, those details come out a lot. Quantizing position will do something similar, but instead of rounding the values, it will round the actual XY position and will result in this kind of pixelated view. So those are both super handy, and I will note that originally I found out about this limit top usage and also a similar application from one of Electronaut's tutorials. So I believe it was called Generative Blueprints. He used the limit top to round and quantize some noise, which I thought was cool. But I think this is a more interesting application. So anyway, thank you to him for the original idea, and let's see what we can extend it with. So I'm going to also just drag and drop these parameters so that I have them, and I'll call this terrain quantize position step and terrain quantize value step, which is great. And then I'll open my parameters. I want both of these to be pretty low at the moment. And that's fine. Okay, so now we have something that we can use with our jump flood algorithm. And I guess first it would probably help to talk about what a jump flood algorithm actually is. So a jump flood algorithm is actually pretty simple. It is something you've probably come across before in the Voronoi diagram context. So everybody's probably pretty familiar with this. Voronoi diagram is when you take an area, you drop some points on it, often randomly, and then you partition that space based on which point every pixel in space is closest to. So this polygon encloses all of the pixels that are closest to this point in pixel space. This polygon encloses all of the pixels that are closest to this point in pixel space, so on and so forth. And so this leads to a very organic looking partition of space. but it requires us to know all of the individual coordinates of our points, which is impractical if you're thinking about using a texture to actually be the source, or the target rather, I guess, of the distance functions. So what the jump flood algorithm does is provide us a way to, instead of using points and then creating polygons that enclose all of the pixels closest to a given point, it will allow us to use edges and partition the space based off of which edge a pixel is closest to. We will see that, and it'll make a lot more sense in just a second. But before I do that, I want to go through and just mention the component that we're going to be using, because, well, it is simple. There is a very, very efficient implementation of the jump flood algorithm that we can grab from GitHub, and that's going to be way better than any implementation that you or I would be able to do ourselves. So I'm just going to use that because the point of this tutorial is using the algorithm itself, but not necessarily coding the logic. So we'll look through the logic in a little bit more detail beyond what you see here, but we're not going to be programming it ourselves. We are going to be using a component from David Braun, who is great and super skilled and has created so many things that are super helpful. So you can just go to his TouchDesigner shared repository, go to the tops, and grab the jump flood. Wherever it is, the jump flood tox. We can just download this. And then drop it into our network. Now, we don't see anything, but that's because we need to drop in an edge for it to work with. And we probably want our edge to be a little bit more sharp. So I'll quantize our values a little bit to make these edges sharper and give us a very clean boundary to work with. Now, let's take a look at the output before we look at what's going on under the hood. Okay, there we go. So as we can see here, and I'll actually put another edge down to make it even more clear, make sure that comes through in the video. What we're looking at what we're looking at is space that is being partitioned based on how close a pixel is to these edges. So as our edges or pixels get closer to our edges, the pixels, sorry, that was not right. Cuts. So we can see a little bit easier what's going on by taking this top component, or actually maybe not doing that. Maybe we will just grab this edge, put a composite down, and then put these over each other and take a look at that. All right, so now we can see what's going on pretty clearly. We are partitioning our space based off of the edges. So here, for example, we can see these edges enclosing this boundary, and here we can have our space partitioned based off of how close the pixels are to these boundaries. It results in a pretty cool effect, and one that is immediately reminiscent of different maps. And actually, if we go back to the Wikipedia page, if we go back to the Wikipedia page, all right, and actually, if we go back to the Wikipedia page, we can see that this game developer, Paradox Interactive, uses a jump flood algorithm to render borders between countries and provinces. And I guess this is one that they did it with. So, immediately, we can already see that there's a direct application of this algorithm for making maps. And that's great, because that's what we're using it for. So, now, let's take a look a little bit more in depth at what's going on in here. Like I said, we're not going to be doing the programming, but we can at least understand a little bit about the programming logic. So, let me get this over here. Let's see what we can see. So, first of all, at a high level, what's happening? For each step size, k, we run one iteration of the jump flood algorithm. So n is our number of pixels, and then our step size is going to be an exponentially decreasing function of those number of pixels. So we'll start with step size of half the resolution, then a quarter of the resolution, and exponentially step down to a step size of 1. Every iteration, we're going to look at the neighbors of our pixel based on the step size. So that means that for a very high step size, like n over 2, the jump flood algorithm is going to be looking at a neighbor very far away from the actual pixel location. And when the step size is 1, it will be the next door neighbor. And it will compare the values of the current pixel and the comparison pixel. If it's undefined, that means that it hasn't been evaluated yet. But if both of them are colored, then it's going to check and see if the colors represent the same amount of distance away from an edge. And if that is the case, things will be the same. And if it's not the case, then they will switch because it means that the neighbor pixel is closer to an edge than the current pixel. So the iterative step sizes allow you to hone in and optimize for each of the specific edges in a performant way, and it doesn't require you to do many passes at full resolution. That said, it does require a decent bit of computation, so it's not the fastest thing in the world. However, we have a GPU implementation that we're going to be using, and that is why we're not going to program it ourselves, but use the nice hardware accelerated component that David Braun has already created. We'll see that that component is actually a port from a 2017 Pixel Flow implementation from Thomas Dewald. That's used in processing, but processing can use shaders and does for some more advanced stuff. So you can actually go take a look at the Pixel Flow library itself and get some other cool stuff that you can port to TouchDesigner if you're interested. But yeah, like I said, right now we're just going to take the implementation that David Braun gave us. And what he does here is essentially an edge detection step where we're actually deciding which part of our image is an edge. There's a bit of processing here. In this step, we're actually doing the jump flood algorithm itself. You can see that we do several passes. I think in this case, 10 passes. And at each pass, we look at the neighbors. The neighbor step size is determined by So that by this array, which as we can see here, is indeed an exponentially decreasing function of our resolution. So this represents our step size. So essentially each pass in that shader is going to sample one of these step sizes from this vector. Use that as the step size to determine what pixels it samples for the neighbor. Do the comparison that we just talked about, and then output the result. Then the outputs of this component are one sign distance field. So if we press D while the viewport's open, we can inspect the pixels, and you'll see that the values go way up the further you get away from the edges, and are 0 right when you're at the actual edge itself. So this is, again, just the sign distance field. If you look at the parameters and you change this multiplicity add, that will kind of control the fall off of this distance field, which is useful in some applications. Here we have the jump flood result distorting UV space, so we can use this to remap images or other things. And then finally, this would be basically just using this UV map to remap the image, which actually can be a pretty cool effect too. We'll use that. So that's the quick tour of the jump flood component from David Braun. There is really a ton to learn from all of his components, this one included. I'm not going to go through all of the different intricate things that he does, but for anybody that is interested in digging deep and picking up some golden nuggets, I highly recommend just like fully picking apart this component. But I mean, really, just go through this entire TouchDesigner shared repository, and anything that strikes your fancy, just dig into it and see what you can find. I've learned a decent portion of what I know from that TouchDesigner repository. So, anyway, now that we have a bit of an understanding what's going on with our jump flood algorithm, we can do a quick application to start to develop an intuition for how to use it. So one cool thing that I like to do is if we just grab this null and then a displace, and then maybe we grab an image. I've been recently using some images that I created in Midjourney. They are some cool 3D wall art textures that I actually generated using like an image, or that I generated using works of my own as source images. So I don't know, I think it's pretty cool. I'm just going to use this as our image to distort today, but obviously use whatever image you like. Close that. Yeah, so one pretty cool thing is simply to just use this displace, not even do anything super crazy with it, but just drop an LFO. Make the frequency like 0.1, and just drop this on for our displace weight. And the amplitude can actually stay at 1. That's totally fine. Make the frequency 0.05. And already we kind of have this really cool distortion effect where our image comes into and out of focus, And when it's out of focus, is really restricted along these edge lines, which is already something that's not very easy to do using a lot of other techniques, and is looking pretty clean with this. So that's one. Another is to use this UV remap. Take the same, use select to save memory, and just do the same thing here. So take a displace, wire that in, and we're seeing a little bit of jittering, which is expected with a partitioning algorithm like this. So what we can do is maybe just add in a quick little feedback loop. Do a composite, make it an over, drop this down, and yeah, we're seeing a lot less of the shimmering, and it's actually a pretty cool distortion effect that's happening now. Maybe we'll copy and paste this LFO, we'll change the frequency to be like 0.1, we'll drop this on here. And that's, again, already looking pretty cool. Make sure to copy and paste this feedback pulse parameter so that it resets when we want it to. And then you can start to, I don't know, maybe wire this in. So maybe we're now displacing multiple tiers, multiple different ways. And as you can see, this is already kind of kaleidoscoping in a pretty cool way. And then every once in a while, when the periods align right, it should have a perfectly clear view very briefly. So yeah, like I said, this is kind of a ancillary effect to the main generative maps. I'm actually going to stop this here for right now, just to keep this tutorial on the shorter side. But what we're going to do next time is keep the jump flood algorithm, use it in a slightly different way, and actually see how we can apply several of these to create some different layers out of our terrain, and then recompose those layers to create the map effect that you saw at the beginning of this. So yeah, I'm going to leave it here for now. Thank you to all my Patreon supporters. Really means the world. You guys are great. I will look forward to seeing the work that you guys create using some of this stuff. I love it. And yeah, I'll talk to everyone soon.